So, dear students, let us continue our discussion. Today, we will get to know how exactly the charges flow inside the metal. Okay, you all know that charges flow inside the metal. That is what gives us the electric current, right? But we do not know how exactly the flow, how exactly they move inside the conductor. Okay, so today we will get the detailed idea about the exact movement of electrons inside the conductor. So let us assume a conductor, say this is the conductor of area of cross section A, length L, so and so, so and so. Okay. Now, how does the internal structure or internal arrangement of atoms and electrons look like inside the conductor? So, I have given you the clue in the previous classes. The arrangement look like series of atoms placed with certain interatomic space left. Okay, and that is what the arrangement of atoms. They are situated in their lattice with free electrons revolving in the free space, which means the interatomic space, interstitial space, which you call. Now, this is how the atoms look like inside the metal. Okay. This is a magnified view, okay, and I have just drawn the two-dimensional one, and this is how it looks in 3D also. Here, there will be atoms, here, so there will be atoms. Now, this is how the arrangement will be in most of the solids. You know that there exists different kind of arrangement, crystals, non-crystals, all those things. I am not going deep into it, I am just considering the metals now. Now, what make metals good conductors? The existence of free electrons. Where do they exist? The free electrons in the metals. Okay, the difference of non-conductors and conductors, okay, is as follows. In non-conductors, every atom will have their electrons revolving around their parent nuclei itself. Okay, we have discussed about it, right? We have actually got to know about it. So, if say you have an atom with 10 electrons, all 10 electrons revolve around the nucleus of that particular atom, and this also has 10, so all 10 revolve. So, in this way all the electrons have the electrons revolving around them, and no electrons are free outside here. Okay, that is how non-conductors look like or insulators look like. But when it comes to conductors, few of the electrons, okay, will be free from the parent nuclei. Okay, say from this atom one of the electron will be free, and that electron, okay, will be free from all different atoms present. Okay, so this is how we call this as a pool of electrons, right? So you have abundance of free electrons when you take a conductor, right? Because these electrons are out of their atom, okay, but not out of the entire metal. They are out of their atom and are roaming freely in the interatomic space, and obviously while they move they hit different atoms, right? Now every atom has lost electron, so we can call them as ions, right? Since it has lost an electron, every atom at this lattice can be considered as ion, because its negative charge is roaming somewhere in the interatomic space. So this electron which has come out of the atom in a conductor will be freely moving in random directions. Okay, different electrons in different directions, totally random. Now, See, this is the situation even when we are not applying any potential difference. Okay, means we have not connected this conductor to any battery. This is just just a piece of metal considered, okay, a conductor considered, so with no external battery, nothing, it's just a piece lying there. But internally it's very active, it's very dynamic. All the free electrons will be moving very randomly, okay, very randomly. The order of this velocity of the electrons is very high, okay, and the velocity of the electrons due to this kind of random motion is called thermal velocity, okay. Why do we call it as thermal velocity? Because see, when you want these electrons to move randomly in the interatomic space, they need energy, right, isn't it? So, where does that energy come from? That energy comes from the surrounding temperature or the heat provided to the conductor from the surrounding, right. So, that temperature itself is what provides the electrons energy, and that energy, obviously electrons can have energy only in the form of kinetic energy, no other possibility. So, they move with higher velocity when they are subjected to higher higher temperature, got it. So, this velocity with which the electrons move randomly in the interatomic space in the absence of any external potential difference applied is considered as thermal velocity. And as I informed you, thermal velocity is of very high order, which is 10 to the power of 5 meter per second, okay, very high order in regular temperatures, okay. 10 to the power of 5 is 1 lakh meter per second, right. So, very high velocity when it comes to thermal velocity, right, the random velocity. But this thermal motion of electrons, random thermal motion of electrons will not give a net current in the entire conductor, because they are not moving in one direction. So, at any instant considered, the resultant of all the velocities of the individual electrons will be equal to 0, okay. So, which means if one of the electron is going like this, the other electron will be going like this, right. We know how to calculate the total current, right. Capital Q is equal to Q plus Q1 plus Q2 if you have two charges, right. If two electrons are going, one going like this, the other going like this electron gives you a charge of minus Q, and this gives you a charge which you should consider as plus Q. So, minus Q plus Q becomes 0, okay. You refer to the previous lecture, you will get to know. So, the resultant velocity at any instant chosen inside the conductor for free electrons will be 0. That gives us the idea that, okay, when we do not provide any potential difference, even though there exists velocity to the individual electrons, the net velocity becomes 0, and hence there will be no current in the conductor when we are not providing the potential difference. Clear on that? Okay. So, this is when we did not connect the potential difference, or say battery, when we did not apply the potential difference, or in other words, when we did not connect the conductor to a battery. Now, look at this. The actual current flow shall be studied now. Let me connect this conductor to a battery now, okay, like this. Okay. When I connect the given conductor to a battery, what I am actually doing? I am creating the potential difference, right. So, this is one end, this is the other end, this is connected to positive terminal of the battery, this is the other end which is connected to the negative terminal of the battery, and hence I have created a potential difference in the conductor. And hence, due to the application of potential difference, now the electrons starts to experience a force in one direction, right. Look at this. What is the direction in which the electrons experiences the force? So this is positive terminal of the battery. So this is at higher potential. I can say this end is at positive potential. This is at lower potential. I can say this is at negative potential, and hence I can consider the existence of electric field inside the metal in this direction, right? So due to the application of potential difference, a uniform electric field will be set in this direction now. So this electric field will exert force on electrons, because we all know that electrons are charged particles. Any charged particle in the external electric field will experience force. Now all these electrons starts to experience the force. So what happens after they experience the force? They tend to move in the direction of force. Before that, which is the direction in which they experience the force? See, field is like this, right? And every electron, since they are negatively charged particles, they will experience the force exactly in the opposite direction, right? So all the electrons, individual free electrons, will experience a force like this. Okay, but that doesn't mean that they leave their random motion and I have applied the electric field and they all start to move like this linearly. No, that doesn't happen. That is where the actual physical thing is. See, now what happens is, even though we have applied the electric field, this electric field that we have applied is not so strong that the electrons leave their random motion and simply come in the direction of application of force. No, that doesn't happen. Instead, all the electrons will be in their random motion, and along with the random motion, they tend to drift in the direction of force. Okay. Now, what is that drifting of electrons? So, electrons are drifting, moving, okay, drifting of electrons. So, now what happens is, drifting of electrons can be considered as such, which says okay, we will take the definition in the form, we include the term drift even in the definition. Okay, the drift of electrons, okay, drift of electrons with a velocity, okay, which we will name later, with a velocity Vd, with an average velocity, okay, with an average velocity Vd in the direction. What is the direction of drift? In the direction opposite to the electric field. Applied electric field E. Okay, this is drifting of electrons. Now, let me give you a clearer idea how does drifting look like. Okay, so you all have heard of drifting in drifting of bikes, drifting of cars and all. Okay, let me take an example of drifting of a car. Okay, say you have open field like this. Okay, and in this open field, a car is moving like this. Now, the direction of motion of car was initially like this. Okay, the car was going like this. This is the path of the car. Now, suddenly what happens is, the driver decides to turn the car suddenly in this direction, perpendicular like this. Okay, but the ground was very slippery. Okay, very slippery ground. Then what happens? He was going in this direction, suddenly he turns the steering. What happens is, instead of car going in this direction, the car now tends to go like this, isn't it? Now it's the resultant effect of initial velocity and the turning of the steering. So here what is happening is, the car is not totally moving in this direction even though he wants to. It is actually maintaining its original direction with a little reorientation, or I can say with a little tilting effect orientation like this. So here the car direction of the car might look somewhat like this in this kind of situation. Okay, the car might look to be like this, but going like this. Okay, the car is actually directed in this direction, but it's actually sliding. Okay, this kind of effect can be considered as drifting. Drifting is normally done in curves, no? So when you take a curve, what happens is, you will be maintaining your path. At the same time, car will be drifting along the path across the road, right? Like this. If this is the direction of the path, when I say drifting, so it will be moving on the road, but at the same time it will be taking a horizontal drift like this. Okay, so it comes, it goes like this, right? Following? This is the actual direction, but at the same time it drifts like this. So that is what is drifting effect. Now, how does drifting affect the motion of electrons? So when it comes to the actual drifting effect, say let me assume an electron which is moving randomly in the absence of external field. I have not applied, I am considering a single electron. I have just erased the entire picture. I am just concentrating on single electron in the entire conductor. So this electron, in the absence of electric field, it will move in a way somewhat like this. It goes, if it finds an atom here or the ion here, it will hit and come back, and if it encounters one more atom here, it goes like this, then it can go like this after collision. So it's a very random possibility. Okay, very random possibility. So this is how the electron might move in the absence of electric field. Okay, this is the described or expected path of the electron. Now, if I apply the electric field, this electron will, okay, say I have applied the electric field in this direction. Okay, this is the direction of applied electric field. So in which direction does the electron experience the force? The electron experiences the force in this direction. It's negative charge, opposite to the direction of field, it will experience the force in this direction. And now you see, due to that electrostatic force experienced by the electron will not lose this path and simply come in a linear fashion like this. No, it will not happen. Instead, under the influence of external electric field, the electron drifts from its original path. Okay, the new path of the electron due to the application of electric field will be as follows. Now it was expected to go from here to here, and now there is a force on the electron in this direction. So instead of reaching this point, the electron will reach a little ahead in this direction. Okay, so the electron will reach this point. Clear? And now after collision with the atom present here, it was expected to arrive at this point. Due to the external field, it will arrive at a point which is little away ahead in the same direction. Now from here to here, it was expected to come here, but it will reach this point. Okay, and again from here to here, it was expected to come here, but instead it will come reach this point. Okay, and from here it was expected to come here, instead it will come here, and from here it was expected to come here, instead it will come here, and from here it was expected to come here, instead it will come somewhere here, and here to here, instead from here to here, and finally it was expected to arrive at this point, but instead of arriving at that point, it will reach this new point. Okay, this is what is the new path of the electron in the presence of electric field. Okay, in the absence of electric field, this is the actual path it follows. In the presence of electric field, the electron follows a new path, which is this dotted line. Okay, clear on this? And now the average velocity. Okay, just a minute, let me verify. Okay, now in this phenomena we need to discuss few technical terms, and now now we can say the electron has drifted in this direction by this amount of distance in certain time interval given. Now you see, we can say we shall define a technical term there, which we can call as drift velocity. Okay, drift velocity represented by v subscript d, small v subscript d. Okay, drift velocity of the electron, free electron, is defined as the average velocity with which the electrons drift. The average velocity with which the electron drift. But let us put some more technical points in order to complete the definition. In which direction is it drifting? Okay, electrons drift towards, right, will be connecting the conductor to the battery, right? So electrons always drift towards positive terminal of the battery, isn't it? Because it's at higher potential, towards positive terminal of the battery. Okay, why is it moving? Because we have applied electric field. How does the electric field is applied? Just by connecting the battery, that's it, nothing else. Okay, towards positive terminal of the battery by the application of electric field. Okay, this is what is drift velocity. Clear on this? Very easy, which is represented by small v subscript d, drift velocity. Now let us see one more important technical term here. Before that, let me give you the idea of the magnitude of this drift velocity. Drift velocity is very less when compared to the thermal velocity of the electrons. Okay, very less. Normally drift velocity is in the order of 10 to the power of -3 to 10 to the power of -4 meter per second. Okay, so this is the order, very less, 10 to the power of -2, -3, -4, very less when you compare to the actual thermal velocity of the electrons, which is 10 to the power of +5 meter per second. Following? So it's very less drift velocity which we can provide to the moving electron inside the given conductor. Next, another important technical term regarding this phenomena is relaxation time. Okay, relaxation time is represented by which is used as torque in your previous class. Yes, it is tau. Okay, tau is the symbol which is used to represent a relaxation time. Okay, you can consider this is the small tau, there it is capital tau. Okay, so tau is the relaxation time. Then what is that relaxation time? Okay, where you can simply assume it as it is the time for which the atom the electron is relaxed, which means when is the electron relaxed? When it is not undergoing collision, it is relaxed. So we can define relaxation time as the average time spent by an electron between two successive collisions. Okay, average time. Clear? So we can define relaxation time as the average time spent by the free electron between two successive collision. So between two, I mean, yeah, from here till it reaches this point it was free, right? So this is the relaxation period of the electron. But here the relaxation period increases, 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 decreases, increases, decreases. It can happen randomly, but we will take the average of all those times, and that is what is, we will take that as relaxation. The average time spent by the electron between two successive collisions in a conductor is relaxation, and this relaxation time is of very small order, which is 10 to the power of minus 14 seconds. Okay, an electron spends at an average of only 10 to the power of minus 14 seconds between two successive collisions. This is the order of relaxation time. Okay. Now let us see the mathematical expression for drift velocity. So now we will take the expression for drift velocity Vd. Okay. There is a small derivation, but that derivation is not included in your board syllabus, but simply I will give you the glimpse of it, and the final expression will be important for you. Okay. So it is quite easy. See, drift velocity can only be seen under the influence of electric field, right? If no electric field, no drifting, and hence no drift velocity. Okay. So an electron experiences a force of E due to the application of electric field, right? F is equal to EQ, remember that E is the charge of an electron now, Q is equal to E, and hence an electron experiences a force of F is equal to E, right? When it is when the force is expressed mechanically, we can say F is equal to ma, right? So where m is the mass of an electron, so ma becomes equal to E, and hence A becomes equal to E by m, right? But now what is A in the direction of in the direction opposite to that of electric field, which means like this. What is the acceleration of the particle in that particular direction? A we know that A is equal to V minus U by T, right? So it is V itself is the drift velocity acquired by the particle minus U. Initially the particle did not have any velocity in this direction. Okay, it was moving randomly, but it did not has any velocity in particular direction. So initially drift velocity is 0 divided by time it takes will be equal to average time now. So average time spent is nothing but the relaxation time tau. So Vd minus 0 by tau becomes equal to E by m, and hence we will get the expression for drift velocity is equal to small e, let me write small e first, E by m into tau. Okay. Anyhow, you will not have the derivation of the expression, but you just make sure you know how it comes. But this expression is very important for us. Vd is equal to E by m into tau. Now you can see which are the factors which decides drift velocity, right? Look at this. E is the charge of electron, which can't be varied, fixed. M is the mass of electron, which is again a fixed quantity. This capital E is the one which we can decide, right? which is the electric field. If we apply more potential difference, we can get more electric field, right? So E we can decide. So I can say more the electric field, more the strength of electric field that we apply, more the drift velocity of the electrons will be. Okay, I can conclude this much from the expression. Okay, now this tau is internal one. Okay, relaxation time is internal property of the material of the substance, and you can interpret on what factor does this tau depend on. Tau, relaxation time, depends on the temperature. Okay, think over it. I have told you that the thermal velocity, the random velocity acquired by the electrons is purely due to the temperature of them or the heat in them, right? So that is why we call that as thermal velocity. Now you increase the temperature, the random motion increases. When the random motion increases, the relaxation time decreases, isn't it? The relaxation time actually decreases because it moves faster randomly and then hits more and more atoms in less time. So relaxation time decreases when the temperature increases. Okay, this is an important point, make note of it. Now this is the expression of drift velocity, and we'll see one more expression for current, okay, electric current in terms of drift velocity. Okay, expression for current I in terms of drift velocity. Okay, this is again a derivation which is there in your reference book, but again it is not included in your board syllabus, so I am not going to derive it. It is again a little complex one, so and it takes time, so I do not want to spend time on it. I will be directly going for the formula, which is as follows. The expression for current in terms of drift velocity is as follows, which is I is equal to N E A V D. Okay, N E A V D, where many terms are familiar to us. E is charge of the electron, A is the area of cross section of the conductor considered. Okay, area of cross section of the conductor A, and Vd is drift velocity. Now what is this N? N is the number density of electrons. Okay, or we can also call that as electrons, number of electrons, which is number density is number of electrons per unit volume. Okay, the number of electrons present per unit volume is this small n. Okay, so this is the, because you need to imagine now. Okay, even though a conductor is small, when you magnify it to the scale of a room, okay, or a building, the entire building, then you start to see what is actually happening inside it. The atoms will be fixed in their lattice. These free electrons will be moving randomly in the space between the atoms. Random motion will be occurring. You apply the electric field, they start to drift under the influence of this electric field, and now you consider unit volume there. Okay, unit volume means 1 meter cube, which is theoretically not possible. It should be a large conductor. That's fine. Okay, per unit volume is the term which is important here. Okay, in 1 meter cube, how many electrons can you find? Okay, if it is the volume of 10 times lesser, then you take 10 times lesser number of electrons. Okay, that's fine. So finally, what you should obtain is number n, which is number of electrons per unit volume. Okay, don't need to worry. Whenever it comes to numerical problems, this value of n is provided to you. Okay, you don't need, you won't get a situation where you need to actually calculate n like that. Okay, so don't need to worry about it. So, but these two formulae, they are very important. This is the expression of Vd. This is the expression of current in terms of Vd. Okay, in terms of Vd, which is NEA Vd. N is number density of electrons. E is the charge of electron, A is the area of cross section, Vd is the drift velocity. You should remember these two formulae, very important. Okay. And we have one more technical term to discuss now, which is called mobility of free electrons. Okay. Mobility of free electrons. This quantity is represented by symbol mu, and this quantity represents how free the electrons are to move under the influence of electric field. Okay. See, in some materials you apply very less electric field, they tend to acquire more drift velocity, they tend to drift faster. In some materials you apply large electric field, the drift that you see is very less. So, that depends on the property of the material chosen. Okay. And so, in order to get to know that property, we define this term mobility of free electrons, which is defined as mobility of the free electrons is defined as the drift velocity acquired by the free electrons per unit electric field. Okay, per unit electric field. So, this is what is defined as mobility of the free electron. Now, let me write the expression for mobility. So, that mu becomes equal to, see, it is drift velocity, which is Vd per unit volume, which means I can put per unit electric field applied. Okay, electric field applied. So, whatever the amount of electric field we apply, we just need to divide it, so that we get Vd by E, which itself is our mobility mu. Now, you get the expression for you get the unit of mu. Unit of mu will be, the unit of Vd is its velocity finally, meter per second. Unit of electric field, you have two of them, right? One is volt per meter, the other you have Newton per coulomb. Let us choose volt per meter here. Both of them are valid. Okay, for electric field, from first chapter the SI unit that we see is Newton per coulomb, and from the second chapter we see that it can also be expressed as volt per meter. Okay, from the expression V is equal to minus dV by dx. Fine. Now, E has the unit of volt per meter, and hence meter cancels. So, the unit of mu mobility is volt per second, and you get the dimension of it. Okay. Oh, sorry, I made a mistake here. Just a minute. It's not volt per second. See, it's in the denominator now. So, denominator comes to the numerator, per volt into meter it happens, right, from the denominator when it comes to numerator. So, there it becomes meter square per volt per second. Okay, this is the unit, or you can also express it in terms of Newton per coulomb. Meter per second, the Newton per coulomb comes to the numerator, coulomb per Newton it happens. Okay, when you are meter per second will be there. So, Newton per coulomb comes here. So, that becomes coulomb per Newton. Okay. So, these two are the units of mobility. You get the dimension of the term mobility. Next, an important derivation, which is the expression for electrical conductivity. I am simply keeping it as conductivity. Okay. For conductivity of a metal, what is the symbol for conductivity? For resistivity is rho, for conductivity it is sigma. Okay. In terms of relaxation time. What is relaxation time represented by tau, and number density. Number density is represented by n. So we need to derive, okay, this derivation is very important and asked in boards repeatedly. And now we need to derive the expression for sigma conductivity in terms of tau and n. Okay, we need to connect sigma with tau and n. Okay, so initially whatever the initial part, diagram and all, they have to be written, drawn. So let us take assume a conductor of area of cross section A and of length L, okay, to which a potential difference of V volt is applied, and hence an electric field of E is set inside the conductor, and under the influence of this electric field, let the electrons drift with the velocity of Vd. Okay, all these terms we have already discussed, and that is what I am representing pictorially now. So Vd, let the conductivity of the given conductor be sigma and number density of the given conductor be n. Okay, these are the considerations and diagram of the given arrangement. So now let me connect the terms. First let me write the expression for Vd. Okay, the expression for drift velocity is given by we have discussed about it now, right? It is E by m into tau, right? This is the expression of drift velocity. Now we will not stop here. So when the electric field is applied, let us assume I is the current set up in the conductor. Okay, I is the current set up in the conductor, and hence let me write the expression for current in the circuit in the conductor given by I is equal to N E A V D. Okay, N E A V D is the current in the circuit, where N, you know that it's electrical conductivity, N is the charge density, number density, E is the charge of an electron, A is the area of cross section, Vd is the drift velocity, right? We know that. Now let me express this I because we need sigma, no? We have a connection here. If I take A here, this will become I by A, right? So let me take A into the LHS, and hence it becomes I by A is equal to N E. Now Vd is left here. Let me substitute Vd is equal to E by m into tau here. Okay, instead of Vd, now I'll put E by m into tau. And now what is I by A? I by A, current per unit area of cross section. Last session, I by A is charge current density J, okay, which is a vector quantity which we discussed in the last class. So I by A is equal to J is equal to what happens in the LHS. So N I can put E into E squared, capital E remains as it is, tau will remain, divided by m. Okay. So now we have J is equal to N E squared E tau by m. What is this J equal to? Okay. In the last session we have discussed, that's an important derivation which we have done in the first session of current electricity. We all know that J is equal to sigma E, right? Remember that formula? J is equal to sigma E, which is equal to N E squared E tau by m, right? Now shall I cancel this E and E? Electric field, both are one and the same, I can cancel them. Finally what is left here is sigma is equal to N E squared tau by m, and this is the required result for us, where we successfully connected sigma, the conductivity of the metal, with the relaxation time tau and the number density n. And how is it dependent? Sigma is dependent on dependent directly on n and on tau. So sigma is directly proportional to n and sigma is directly proportional to tau. Okay. So if you have the value of tau greater, okay, then conductivity will also be good. Following? When will the value of tau be greater? When the temperature is less, right? When the temperature is less, the thermal agitation or thermal velocity of the electrons will be less. So they will be undergoing random motion, but with less velocity this time, and hence the value of tau increases, right? When the temperature decreases, tau increases, isn't it? It takes more time to reach from one point to the other point. So tau increases and hence sigma increases. What is sigma? Sigma is conductivity. So that is how we can relate. When the temperature is lesser, tau increases and hence conductivity of the substance of the conductor increases. Okay, particularly conductors. We are discussing about conductors, right? So that is how we can say at lower temperatures the metals are good conductors, and at higher temperatures metals are not good conductors. Okay, we can't say them as bad conductors, not better good conductors as of the when they were when compared to the metals, the same metal in lower temperature. Okay, this is an important derivation.